So let's start by building up our toolkit a little bit with key terms that we're going to be using throughout the semester. So I know it can be tedious to just have a bunch of terms thrown at you. So what I'll be doing is kind of discussing these, what they mean, how they're used. Not going to be giving each one the time that it deserves to fully understand it, but what we're doing is getting you familiar with a term enough that it kind of starts to build connections in the brain. Then later in the semester, as we put all these pieces together, it's got some network already formed that it can build off of, right? So the learning science suggests that introducing terms with enough information and context to start to build those networks makes it easier to fill in that information as we go along. So here we go. So we're in a course on statistics. I mentioned that's the set of tools that we use to analyze data, organize data. The first term that we have is statistic. So statistic is a number that describes a sample. It's tricky knowing where to start because everything builds off of everything else, right? So a statistic is telling us something about a group of data that we have. And so a descriptive statistic is simply that. It is telling us a characteristic of a sample of data of, we've got a spreadsheet and we can calculate the average, the mean of a variable. Maybe it's your GPA coming into this course. Now, that average that Excel tells us, that's a statistic, a descriptive statistic. So we would say in this class, the average GPA coming in is whatever the number is. That's a descriptive statistic. There's a different type of statistic. There's a time when we want to go a step further than descriptive statistics. We want to actually draw conclusions from our data and help inform those better decisions we've been talking about. This is when I talked about kind of the core question that we usually want to answer. What would my life look like if I had stayed on the asparagus farm? And we talked about why that's so tricky. That's a counterfactual that never happened, right? We don't know exactly what my life would look like. So the best we can do is kind of gather data from the best comparisons we have and make conclusions based on that. When we make conclusions based on it, that's called inferential statistics. We're not just describing data then, we're actually trying to draw conclusions from it. So this is a step further. It's almost always quite a bit trickier than simply describing what's going on in a data set. To be able to draw conclusions from it, we have to really know what's going on with the context of the data, and we have to make some assumptions. So if we want to say something about the students in this class based on the average GPA coming in, maybe we do a survey of the class, we get this data, and the number that Excel spits out is 1.9 as the average, the mean of GPAs coming into this class. Okay, well that's a descriptive statistic. For us to draw a conclusion from that, we're going to take that next step to inferential statistics. We're going to try to better understand what's going on with it and use that to help us make decisions. Now, 1.9 seems pretty low to me. I don't know. We would want to take a look. Maybe we have some students coming into this class who don't actually have a GPA yet. So if that's entered as a 0, that would pull the average down, right? So we would want to look at things like that. If we're going to try to draw conclusions from it, we have to do a better job understanding the data than to just be able to say, oh, 1.9 is the answer. That's the number. That's what we care about. So that extra step of trying to understand what's going on so we can make conclusions from it, that's called inferential statistics. And so we start with descriptive statistics, and we then start to think about this inferential side. How much can we actually draw conclusions based on this? To really get into inferential statistics, there are a lot of additional higher level courses that you could take, including within our econ department. But a lot of that will be beyond the scope of this course. But well within this course, one of our learning objectives is for you to be able to recognize descriptive sort of claims and these claims that are based on inferential elements, causal elements we often call them, because we're trying to draw a conclusion that X causes Y, and that is a lot trickier than just saying there is a relationship between X and Y. So we'll talk about that quite a bit as we go along. Again, we're just building this foundation for now. So what are some other key terms that we need to think about? We need to be thinking about kind of where this probability and statistics come together, which is in the world of sampling. So sampling is when we're selecting certain data out of a bigger group of data. Now, the bigger group of data we would call the population. So if we're talking about the population of the United States, it means every person living in the United States, right? That is the population. Now, the Census Bureau conducts various surveys. They sample, they randomly select a certain number of people, maybe 20,000 people, and ask them questions about their employment or their housing. So there's the American Community Survey that's asking a lot of questions about where you live, your transportation methods, your family, all kinds of things like that. There's also ones that are looking at your employment, your wages, whether you're unemployed right now. So what the Census Bureau is doing is they're sampling. They're randomly picking some people out of the US population. Now, if you are randomly picking people out of a big population, if you have enough people in your sample so that you have the general characteristics of the population represented, we would call that a representative sample. And so that's often the goal when people are conducting surveys, whether it's the US Census Bureau or Pew or the pollsters who do political polls. They're often trying to get a representative sample, meaning they randomly pick enough people so that their sample looks a lot like the general population. A reason you do that is because it's a lot easier to make good inferential statistics based on a representative sample. But we'll get there and we'll describe kind of why that is. Now, we already mentioned that a statistic is a number representing a property of the sample. There's so you can think of the statistic being related to the sample, right? We know that the sample is part of a broader population. So there's actually a true value for the population. We call that a parameter. And I usually think of that as kind of like the target. That's what we're aiming for. That's what we want to figure out when we're using statistics. Now, we're almost never going to be able to tell exactly what the parameter, the true value is. So if you're thinking about the education level of people in the United States, there is a true value that tells you the distribution of education levels of all of the people who live in the United States, right? We can sample 1,000 people in the US and get a sense of what that distribution would look like. This many people have below high school, this many people have a high school degree, this many people have some college, this many have a bachelor's, this many have a master's, this many people have higher or terminal degrees. If we sample 1,000 people and it's a representative sample, that might start to give us a pretty good idea of what the parameter value would be, the actual value of how many people have each of these different levels of education in the US. But we don't know exactly. The true parameter value is coming from this population, and usually we don't know exactly what that is. And that's one of the tricky and sometimes exciting parts of statistics is we often don't know exactly what the truth is. We're trying to get our best guess at what that will be. That requires some assumptions, and we'll learn some kind of things to look for and tricks that help us figure out if our statistic based on a sample might be doing a good job approximating the parameter that is the value for the population. Now, when it comes to data that we've gathered, we often organize those as variables in a spreadsheet. And so usually what we will have in a spreadsheet is we'll have columns going across the top that have different variables in them. The first one might be an identifier just to keep track of each person in our data set, right? Maybe the next one is your name if we're gathering names. Maybe the next variable would be what state you live in. Maybe we would have a variable about what your GPA is if you're a student. Variables can take all kinds of different forms. Something like a GPA is a numerical variable. It's a number. For each person in our data set, that numerical variable is going to have a value, a number value, something we could put on the real number line. So your GPA could be 1.2, it could be 3.9. Those are numbers for different people, right? Now, something like a name, that's not a numerical variable, that's a categorical variable. That's something that each person within that data set is going to fit into a special category. Something like name, everyone, hopefully, in your sample has a unique name. If they don't, maybe you have 2 John Smith in your sample. Well, that means you have 2 people within that category have the same value for that variable. That's one reason why you often start with an identifier variable, something you know is going to be different for each person, so you can keep track of exactly what's going on in your data. Categorical variables often take a form of, if you're surveying students, what year are you in college? Are you a freshman, a sophomore, a junior, a senior, or other? Those are 5 different categories you could fit into, right? Freshman, sophomore, junior, senior, other. So that's a categorical variable. It's not going to be unique. There are going to be a lot of freshmen. There are going to be a lot of different sophomores, etc. It's not unique to each person in your data set. It's a categorical variable because everyone's going to fit into one of those categories, and that's how we describe it. We describe it as people fitting into those categories. So it's different from a numerical value. Now, the tricky part, very often when we gather data, we might say, okay, freshman is coded as 1, sophomore is coded as 2, junior is 3, senior is 4, other might be coded as 5. So if we look at a spreadsheet, we might see numbers for all those people, right? We go down this column under year in school, and we see 2, 2, 4, 1, 2, 3, 5, 2, 2. We see these numbers going down the column. That doesn't make it a numerical variable. A numerical variable is something that has value as a number. You could think of it as, the GPA, it means something to have a 2.2 versus 1.8, right? And we could take an average of those and say, okay, the average is a 2.0, and it means something. If we take the average of categorical variable that's been coded 1, 2, 3, 4, 5, it doesn't really mean anything, especially with that other being coded as 5. If we take an average of these values, it's not exactly clear what we're getting. We might use numbers for convenience sake to organize our data, but they don't actually mean something as numbers. They're just telling us which of the categories people are fitting into. Okay, so we've covered different types of variables. We've talked about samples and sampling, which is the process of gathering a sample from a population. We've talked about data. Some of the very most straightforward statistics that we'll use the mean. Something you're all familiar with, the simple average, add up all of the values, divide by the number of observations, that gives us the average or the mean. Another thing we'll work with a lot are proportions. Proportions are a way to express probabilities. And so if we have 40 different values of students in the class and 22 of them are male, we would say we have 22 out of 40 males in the class. That would be a proportion, that fraction, 22 over 40. And we'll learn as we go on that we could also express that as a probability, a number between 0 and 1, but we'll get to that a little bit later. So those are some of the core key terms. You'll see in our book that there are some sample problems in section 1.1 that go along with these key terms. Our homework is going to very closely line up with what those sample problems look like. Basically, I'm going to give you a scenario and ask you to identify, okay, what is this? Is this the population? Is this the sample? Is this a statistic or a proportion? Basically, put the pieces in the proper order. If I give a scenario, I want us to start thinking about, okay, so this is a sample that we got from this population, and we're using this statistic, which is trying to point us toward the value of this parameter. So that's the sort of thing we're doing. Again, let me know if I can help with stuff, and we'll see you on Monday.